This week we're talking about the article Understanding BCn Texture Compression by Nathan Reed. So this is kind of a summary and hits most of the main points in that article. If you're curious about anything further, I would suggest that you read the original. So first of all, what is this BCN? It's a family of lossy compression formats which are implemented in hardware. And the reason for this is so that they can be used in shaders and things to reduce the amount of memory bandwidth that's required when loading when loading the data that's required to just to render graphics. The BC stands for block compression, and the way that this works is there's 4x4 groupings of pixels, which are encoded in a couple of different ways. They're palette based, but they use 8 to 16 bytes per block of pixels, and that represents either a 4:1 or 8:1 compression ratio when you compare it to 4 channel 8 bits per pixel. And the reason that these things are structured in a consistent format like this, certain specified number of bytes per block, has to do with the way that they're accessed. You need to be able to immediately reference a particular block as it relates to a location on the image. So variable compression ratio or any kind of variance in the amount of data that's used per block is going to be problematic for mapping into that chunk of memory. And additionally, you can cache the information in a single block because often when you sample some X and some Y, it's likely that you'll need the data nearby. For example, if you were filtering this information. So the reason that these types of approaches are becoming more important is because of the large amount of texture data that's required, especially with large resolutions like 4K. There's a lot of samples that are taken, and so we need these high resolution textures. There's more individual textures required for material properties, different modern rendering approaches. And when you look at the advancements in hardware, this is true of CPUs as well, but memory has not kept pace with the computation hardware. So relatively speaking, the computation hardware is becoming faster at a faster rate than the memory is. So any kind of bandwidth reduction that you can get is positive because that bandwidth is a bottleneck in a lot of cases. So the way that these approaches start out is they make this assumption that there's a limited amount of color variation per 4x4 pixel block. And you can see here in this bricks image, there's only a couple shades of tan and brown in each one of these blocks. The way that these things are encoded is in terms of endpoints of a line in RGB space. And then there's a few bits involved in a palette to index into a few different interpolated points along that line segment. So as you can imagine, because that line is linear, you can't necessarily have strongly red, green, and blue values encoded because they don't lie on a single line in that space. So things like text or things like normal maps may have this type of issue where you're pointing in a lot of different directions. You see all three channels are being used, and that is kind of one of the places where this kind of thing breaks down. So to get into the particulars of the format, BC1 is the first one. These are named chronologically when they were developed. Going through them in a little bit of an odd order. It's the order that they're presented in the article. This is basically starting from the simplest and going to more complicated approaches. So BC1 is designed to represent 3-channel data, and it also supports a 1-bit alpha channel. So it uses 8 bytes for a 4x4 block, which averages out to 4 bits per pixel. And what that 8 bits or 8 bytes of data consists of is 2 endpoints, which are encoded in a 565 RGB format. That's 5 bits red, 6 bits green, 5 bits blue. So that is 16 bits or 2 bytes per endpoint. So that's 4 of your bytes. And then for each pixel on the tile, on the block, it's it's using 2 bits to index into this line segment. You can imagine 0, 0, 1, or 0, 0, 0, 1, 1, 0, and 1, 1. So this has issues with smooth gradients, mostly owing to the low precision of the that interpolation, and having more bits in the green channel can actually cause some problems there as well. There's some good examples in the original article if you check that out. And so you mentioned the alpha channel, but it would appear that there's not any more space left. You've got this 8 bytes, you've got 4 for the endpoints, and then 4 for the indexing for each pixel. Well, they make use of an interesting approach here where they call it twofold degeneracy. And basically what this means is the two endpoints can be switched and then still represent the same block essentially. Because those are evenly spaced points, when you interpolate, switching the endpoints would seemingly encode the same information. But the way that they use it is they interpret this 565 format as a 16-bit unsigned integer and compare them for the 2 endpoints. So this comparison determines how the rest of the data is interpreted. So if the first endpoint is greater than the second, the block is interpreted as before, this 2-bit to index into the 4 points on the line. Or if the second endpoint is greater or equal to the second, it's interpreted differently. So there's 3 color values, which is the 2 endpoints and the point directly in between them. And the 4th entry is 4 zeros. That's black with 0 alpha. And there is this constraint that it's 4 zeros, so you can't have RGB and then 0 alpha. It has to be all zeros. So as you can imagine there as well, it sacrifices some of the precision in the palette indexing because you only have 3 points on that line instead of 4. So BC4 is the next one. It's and you'll see how these are used later to build up to the other formats. BC4 encodes a single channel with the same memory footprint. But this single channel is encoded with higher precision. So the endpoints are a full 8 bits. So they can be, that's a single value that can be anywhere in the range 0 to 255. And then the palette indexing is done with 3 bits. So again, higher precision than before. We've got 8 entries in the palette. So this is really good for smooth gradients, noise functions, these types of things, where you've got more variation in the data locally. But you only need a single channel encoded. And again, this makes use of that twofold degeneracy, where the first endpoint is greater than the second. The 8 entries are evenly spaced, and otherwise it's the first 6 are evenly spaced, and then the last 2 are 0 and 255. So BC3 and BC5 are 16 byte per block formats, and that's double what the previous formats were. And the reason for that is because it's essentially the 2 meshed together, or 2 of them meshed together. So BC3 is BC1 for RGB plus BC4 for the alpha channel. And so that's a 8-bit precision alpha. So, or it may be encoding some material property. BC5 is for 2 channels. For example, tangent space normal maps. Something where you might be reconstructing a value in the shader, but that's 2 BC4 blocks kept per block, basically. BC2 is a little bit strange. It's not exactly. It's different than the previous formats because while it keeps RGB as BC1, the alpha channel is just 4-bit values, 16 of them. So that's the other 8 bits, or 8 bytes rather. So these are half precision values. There's 16 levels of alpha that can be encoded this way. And BC3 does a better job by keeping BC1 and then BC4. And you get a better result in the same memory footprint. So this is not really used in practice. This is one of the earlier formats, and it's really not used anymore. So from here, it gets much more complex, and there's a lot of coverage of this in the article. I'm going to just hit some main points on basically what they're doing. There's variable modes, which change the details on the encoding. That's the precision of the endpoints, and then also the precision on the palette indexing. BC6 is targeting 3-channel half precision floating point. Excuse me. And BC7 targets 8-bit RGB or RGBA. Right, so these variable modes are encoded in the first few bits, and that changes the palette size or the precision depending on what the image data looks like. This makes it so that they can encode the image differently for different pieces of the image because the mode selection can be made on a block-to-block basis. Some of them use more than one line segment, that is more than one set of endpoints and palette indexes, and it does this via partitioning. Where BC3 and BC5 do this on a per channel approach. BC6 does this with something called partitioning sets. And so these are basically a mask that applies, it makes the selection based on positioning on the 4x4 pixel block. So again, these get these are more complicated than the original ones. These are more recent. They came out with D3 DirectX 3D or 11 DirectX 11 hardware, I guess. And so they do require some additional hardware features to decode them. So this again makes it more adaptable to different pieces of the image if this fits something better than just a consistent encoding across the whole block. This could be used that way. So there's some more aspects to this. Because the mode selection bits are using some of that memory footprint that you get the 8 bytes per block or 16 bytes per block. They use that degeneracy breaking, the ordering of the endpoints, to eliminate 1 bit of the palette indexes. So that's kind of interesting. And some modes use delta compression. So basically what that's doing is it's keeping the first point at a high precision, and then subsequent endpoints are lower precision deltas from the first endpoint. So if you think about it, that restricts the number of orientations of the segment, but because you have higher precision on that first point and they're positioned relative to one another, you actually have greater precision on the whole structure. You're kind of moving the whole thing around. BC6 treats floating. Yeah, so this is kind of interesting too. Yeah, when it does the interpolation, it treats the floating point values as unsigned integers. So it makes use of the fact that unsigned integers and floating point use the same magnitude order. So the bits towards the beginning, the most significant bit, maps to the higher bits in the exponent, and then the lower bits map to the mantissa. And so when you do this interpolation as unsigned integers, it's actually kind of effectively creating a piecewise linear logarithmic curve. So if you think about it, if you're counting up like you would increment your unsigned integer, you're bumping up that mantissa by some amount until you increment the last bit of the exponent, and then your slope changes. So that's kind of an interesting aspect. So this is a comparison table of the different formats and what they're used for. This is directly from the article. And so this is the complex part, is generating the compressed format. So there's different tools for minimizing the error of the encoded data to try and match the original data as faithfully as possible. And because it's expensive to generate these things, it kind of constrains you to read-only applications. You can't really use this for read-write purposes if you're intending to use textures that way. And so some examples of tools are the NVIDIA texture tools and the D3D11 SDK. So yeah. So if anybody has any questions.
So one thing is, this article is almost 10 years old. So do you know anything about more recent development, like new format or better toolings?
I don't. This is yeah, my the lead guy that does graphics programming at my work recommended that I read this, and we are still using this in the engine. So I guess it's still relatively current.